Hello everyone, it's October 13th. Wow, 13th today. Alright, let's take a look what we have today. We have a medium question. Alright, let's see. I think we're going to do the same thing as yesterday. See how fast we can get it done. If we can get it done, say, within 15 minutes, we're going to try another one. But this is a medium question. Maybe we cannot do it within 15 minutes. I mean, we didn't do it yesterday. Guess it was pretty hard. Alright, construct binary tree from pre-order traversal. Ah, have I done this before? Nope. Alright, pre-order traversal. What's pre-order? Pre-order, given an array of integers pre-order, which represents the pre-order traversal construct the tree and return its root. Guaranteed that there's a possible to find a binary search tree. Oh, it's not binary tree, it's a binary search tree. My bad. With the given requirements for the given test cases. A binary search tree is a binary tree which left is smaller than and the right is greater than. Pre-order traversal, we go, pre-order displays the value of the node and then left and then right. Okay, so 8, 5, 1, 7, 10, 12, okay? All values are unique. All right. Let's do this. It's a tree, so we like it. So it's pre-order. So the root goes first, right? So we know 8. And then after we go with the root, we are going to know the next one will be the left. Actually, we can. Oh, awesome. Oh, nice. All right, so 8, right? And then the next one would determine whether it's on the left side or whether it's going to be the right side because of binary search tree. So next one is 5, so we can say we're going to start building based on 5. So based on 5, we'll build based on 5. And then on a 5, what we see is 1, which is going to be on the left side, so it's going to be 1. And then once that's done, we see a 7, right? We see a 7. So when we see a 7, so we see a 7 because it's based on 5, right? Oh, but it can also be going back to 8. Let's see, 8, 5, 1. So 7. So 7. It's larger than 1, right? So it can be on the right side of 1, but it can be. But I need to check. But 7 is larger than 1's parent, so it cannot be with 1. So it can be with a parent, and I'm going to check its parent is 8. So 7 is going to be here. Once it's done, it's 10. So again, if it's 10, it can be the right child of 7. But we need to check. Oh, this doesn't seem to be easy. We need to check the parent, right? We need to check the parent because the root is 8. So we have to pass in the root value, the parent value, right? The parent value. So hold on. If something is smaller, right? If something is smaller, then definitely it's going to be on the left side, right? The problem is when we have something bigger. When we have something bigger, we don't know which level to go, right? So what we need to do is what should we do in this case? We have 8, right? And then 5 is smaller, so we go to the left branch. 1 is smaller, go left. If it's all smaller, we all go left branch. And now we find something bigger. Now that something bigger could be attached to any one of these, right? And we need to find one that is smaller. Like if it's bigger, then we say, okay, no, it's not me. We go here. and then like it is bigger. It's bigger than my parent. My parent. So like each one record my parent. Okay, I record my parent is 5, so it's larger than my parent. It's larger than me, and it's larger than my parent. So it's not me. I return here. So it's 5. Now I look at 7. 7 is larger than me, and it's smaller than my parent. So it's me, right? It's me. So I go here. Now I have 10. Now look at 7 and I have 10. Its parent is 5. So 10 is bigger than me, so I go here and I compare to my parent, and it's all bigger than my parent, so I can go here. But I cannot, because the grandparent is only 8. How do I go about this? Okay, so we have 8. So 8, 5 is going to be on the left. So we need to find a value that's bigger than 8. Right, this is 10. Wait. Hold on. I think 10. How do I know? 7, that could be something smaller. Right? If it's something smaller, I'll say I'll go here. Right? If anything smaller, we can always go. If anything is bigger, how do we know we need to go all the way back? Go left. 7. Oh my god, I got stuck here. Okay, again, let's just simple case. Let's say we only have 3, right? So we have a root, okay? That one's the first. And the next one, if it's bigger, then we have to check, right? If it's smaller, we always go left, right? If it's smaller, we always go left. And until we find something that's bigger, right? And if it is something bigger, we need to know where do we fit it, right? Where do we fit it? We need to know where do we fit it. So we go here, so we check all the parent, okay? So we say, if we check all the parent, it's bigger than my parent, so it cannot be my right branch. So we go to my parent, and it's 7 is not bigger than its parent. Or do we have to have a list of parents? Okay, 7 is here. So how do we say 10 is going to be there? Because now we're just saying the right? We go to the right, we create a node, we go to the right, and then once we're done, we are looking for the next value, right? So the next value is 10, and I'm at node 7, and 10 is larger than 7, so I can put 10 here, but I need to check my parent is 5. Well, this parent is useless, right? Because I am bigger than you, I'm bigger than a parent, so anything bigger than me will be bigger than a parent. So for this, it shall inherit its parent, right? So the right branch shall inherit this parent. Okay. How do we inherit this parent? So everyone has a parent. If on the left branch, the parent is the real parent, if it's on the right branch, like what if I have more on the right branch? This one, the parent, is going to be this one. So everything on the right branch, the parent is going to be the root's parent. Okay. And what's the root's parent? Well, the root's parent is the root itself. Anyway, so if we say everything on the right branch is going to have what about these? What are these parent? This parent need to be his parent, but that thing doesn't have a parent. That's the root. Or we can set up a parent, right? If we can set up a parent, which is going to be bigger or smaller? Say it's going to be, let's just say its parent is, the value is 8, right? So I'm going to go here, left branch, its parent is going to be 8. Left branch, its parent is 5. And then, now we have 7. The 7 we compare, it's bigger than him, so compare it to the parent. Oh, it's bigger than parent, we'll return here. Again, this one look at 7. It's smaller than the parent, 7 comes here, right? And then it's 10. And when it comes here, it inherits the parent, same parent, 8. Now we look at 10, and 10 larger than 7. So we go right branch, but we also compare it to its parent is 8. It's larger than 8. So we're going to return. So when this one returns, it's going to return here, right? And then this one, look at 10. And the 10 is larger than it, but it's also larger than the parent. So boom, come here. And this is 10. And it's larger than, its parent is 8, right? Its parent is the same as itself, so that's how we know it's a root. So we say, okay, it's the same as me, so I'm going to go here. So its parent is going to be 8, right? And now it's 12. 12 is larger than this, and it's larger than its parent. Should we go back here? But no, because 8 is the root. Huh. How do we reason that? It's on this side of the branch. Well, on this side of the branch, because of the traversal, we already have this, right? So the remainder, it will not go back here. So we can actually see 10 is the new root. That's an interesting thought, right? That means when we transfer here, every time we go to the right branch, from the root, go to the right branch, and each node is its own parent. Everything on the left branch, like this one's parent is this one's parent is this. On the right branch, this parent is this, but no, this parent is itself. Okay, this is the current largest value, right? This current largest value is itself. And if we have this branching here, that this is its parent, and whatever, this is the parent for everything in this branch. How about here? What if I have this? What is the parent of this? It should be 7, right? This, the parent is 7. And if we then have something bigger compared to this, no good compared to this, no good. Okay, because this parent is this. What if we have another node here? What is this? It's not really parent, it's just the value. The biggest value, right? Because these are bigger. So the biggest, what should I put it? The root value. I feel like this is... Am I doing this too complicated? Okay, let's go about the rules again. So, if I'm on the left branch, I take my parent. From my left branch, so if I have node here, I take 7 as my parent, all right? And then if I have something bigger, then I basically will go stepwise, or I'll go back until we find one that can put me, or if we don't find one that's too big, then once we go back to here, then its parent is not this, it's going to be this. Now what about here? What's your parent? If I have something coming here, let's say a 2, right? We can do a 2. So we say we'll do a 2. So its parent is going to be 5, right? It's going to be 5 because that's the value that we need to check, right? So if we go right branch again and find this value is larger than, so whatever we have, like we have this, all of these have the same parent as 5, right? They all have the parent, it's 5. Not only the parent, it's like the value, the smallest value is larger than it. Smallest value that's larger than me. That is the key, right? Smallest value that is larger than me. If on the left side, then the smallest larger value is my parent. If I'm on the right side, the smallest value larger than me is the subtree root's parent, right? And then if I'm on the root, and the smallest value larger than me is none. It's actually none. And then if on the right side, smallest larger than me is this. If on the right side, the smallest larger than me is this. If I'm here, it's going to be this, right? And then if I branch out here, smallest that's larger than me. That's not 12 though. The smallest value that's larger than me is going to be this. It's actually going to be this, smallest value that's larger than me. It's all going to be 8. This one will be 8. Oh, hold on. I think the thing is on the right side and on the left side are different. Wait, is it different? I mean, let's go on the right side, right? So every time we go on the right branch, and if we shift to here, right? And then we'll just construct based on this, because this one is no longer used based on this. So if it's smaller, that will be the smallest value, bigger than me. We don't consider 8 anymore, right? That's going to be all going to be 10. And if we branch here, that's still going to be 10. So basically, every time we go on the right branch from the root, right? Then we don't have to consider the root anymore. So like for the root, we finish construct the left tree. And how about on 5? From 5, finish construct the left tree. We have 5, 1, and 7. Gonna be here, so 5, 7. Then we have a bigger value, and the bigger value is larger than 5. So that means we have finished constructing. No. How do we know we finished constructing? if its parent, it's the smallest value larger than me is not myself, right? Therefore, I'm on the, if that happens, that I am on the left branch. And then finish here, so this one go to the here. Now this can be its new boss, right? And then from here, we can say the smallest value larger than me is going to be 10, right? It's larger than me, it's going to be 10. And then from 10 we'll do 12 is larger than 10, and the smallest value larger than is also 10. So it's the smallest. Yeah, if it's 10 and 10, that means I'm the root. Like, I consider this, it's like a new root, and then I have something larger than me, then I immediately go to the right tree, okay? And if it's something smaller than me, we can go here, and its smallest value larger than me is going to be 10. I pointed to 10, right? And whatever this happens, this is the left tree. And then if something is bigger than 10, we go here. Because it cannot be, yeah, it can be bigger than 10. It will always go 10. Maybe this will work. I don't know. This is more complicated than I had expected. I feel like I'm not thinking this right. But I'm going to just code it and see how it goes. Okay. Good question. Good question. Yeah, I feel like I'm in the little rabbit hole. I just can't get myself out. All right. So form tree, we have pre-order, right? So we're gonna have a what we're gonna have? We're gonna have a root. Yeah, we're gonna have a root. We know the root. The root is going to be tree node val equals pre-order 0. Right? That's the root. And then DFS, not DFS, def build. Right? What do we need? Def build. Well, we need the index. We need a node. Okay, what does this node point to? Well, this node pointed to the parent. So the node pointed to parent. Right, the node pointing to the parent. We can actually just say parent. No, just node. Node pointing to parent. That's going to be a tree node. And index. Index is the next value we're looking at, right? The next value we're looking at. And we need to know the smallest min-max. No, smallest value that's bigger than me. So the min bigger. Right? Min big. It's going to be an int. And build is going to return, I don't know, what does build going to return? Build going to return the index, right? Because it's going to return an index. We're looking at this, so we call this function, we say when I'm at this node, I'm looking at this value, right? And then this will build something, and I will return back is I'm at this. So in the return an integer, which is the next value we're going to look at. The next value we're going to look at. Okay. So, okay. So next value we're going to look at. If index, right? If index, say, So we're gonna go what? I'm looking at current node, and I have an index, right? And I have my min big value, and I want to say if, right? I want to say if node my value dot val is larger than pre-order index. If it's larger, then if my value is larger than the pre-order, the next one must be on my left tree, on my left side. So we can say node.left equal to tree node val equals pre-order index, right? And then we can say build node.left index plus 1. So I use this index plus 1. And mean big. If it's this, that's going to be node val. I'm going to be mean big, right? And then this will return a next index. Right? This will return the next index, which means after this, blah blah blah, this will return the next index, and then we're going to check based on the next index. Right? And we say if the next index, so we have the length, n equals length, pre-order. So if the next index we say if index is equal to n, you're always trying to go to the next index. If index is n, then we return n, right? Otherwise, if no larger than this, the next index is, if it's larger than this, then we'll get the next index. Or we can just say index, right? The next index. So if not, if node value larger than this, then we'll get back. So we'll build this tree. So we'll build the entire tree, right? We handle this. We'll build the entire tree. And we'll return the next index to look at, right? So I think this actually should be index equals. Then we say if node.val is smaller than pre-order index, but this has to be like if we go this way, right, and afterwards index what if we pop, like just don't worry about the index or not index. This just feel very convoluted to me. Can we have an index is easier to handle? What if we use yeah, let's just, if we use a self.index, right? How about we use self.index? So I don't have to worry about this, right? And then because the root of the taken, so self.index will be 1, right? So then we don't have to return anything, because that thing will be constant changing. So we just say if self.index is equal to, I don't know, is equal to n, then we just return, right? means we exhausted the entire thing. Otherwise, we say if node value is larger than this self.index, then we create a left node and self.index plus equal 1, and I'm going to build. Right, I'm going to build. After build, we're going to check. We have to check again, and we do have to check. We do have to check. Yeah, no matter what, like we do have to check. So after building this, we do have to check. We say if self.index is smaller than n, but we can do it this way. If we can say if it's smaller than n, right, and this blah blah blah, and we do the exact same thing, and this self.index, right? So if the node val is smaller than this and it's smaller than preorder, now we can decide, right? So we have something bigger. Now we need to see my parent, right? We need to see my not parent, the main big, right? So we need to see if preorder is the next value, right? So if this value is smaller than main big value for my current node, if it's smaller than that, and it's smaller than the main big value, that means it's going to be my right tree. And we just say node.right equals tree node val equals preorder self.index. Right, so the right tree, then self.index plus equal 1. So I handle this, and I'm going to build node.right, come to the right side, and who is, well, if it's on the right side, that's going to be the main big, right? Because if we keep going this way, it's going to be the main big. Now, otherwise, if it's larger than the main big, right? If it's larger than the main big value, then we need to return. So we can now go here and return to the previous one, right? Return to the previous one. Okay, so we say else is larger than the mean big value, then we just return. Simply return. So we cannot do it here, so we simply return. So we for 10 is larger than 7, and if this value is smaller than mean big, which is not, right, which is not, then I'm going to return, which one return to 5, right? So 5, oh, hold on, 5, we, on 5 side, this is on the 5 side, because 7 is not larger than, so we do this, and then so coming back to 5, then come back to 5, already done, so 5 will go back to 8, now I'll go back to 8, this is done, 8, and now looking at 10, yes, it's smaller than mean big, but it's actually larger than mean big. Here is the thing, if it's larger than mean big, right? If it's larger than mean big and elif, so it's larger than mean big, elif node.val is equal to mean big. That's talking about we are the root, right? If it's this case, then we do the right tree. So node.right equals tree node val equals preorder self.index, right? And self.index is equal 1. And then we're going to build node.right. Now that is now going to be mean big, that it's going to be node.value. But you can see these are exactly the same, so the only difference is Here we can do these two first, right? So note val is smaller than, oh, hold on. We cannot do this because it's on different nodes. Yeah, this has to equal. I cannot, these are different. It's smaller. If it's smaller, we do this. Or, right, if it's smaller, or no val equals. Because if it's big, oh, hold on, let me think. If this one is bigger than mean big, then we cannot do anything, right? So we just say if, yeah, so if this is bigger than, right? If this is bigger than, then we return. Otherwise, we can do these two, right? And then we can build. Now this, if it's this, is if this is we know this is going to be pre-order is larger than mean big, right? If it's larger than mean big, then we return. Then we all have here the value is also larger than mean big, then we cannot return. So it's larger than mean big, and note.val is smaller than mean big, right? If this is larger than mean big, and note.val is smaller than mean big, so that means we're here, and we return. Else is this one is smaller than mean big, or this is larger or equal to mean big, which is fine. So this is the case when we have this, and we'll say mean big if note.val is what? Note.val is smaller than mean big. If it's not equal to, right? If it's not equal to mean big, then we do this. Otherwise, we do note.val. Something like this. Alright? So we build the left tree. If it's larger, then we keep building. And then once it returns, we can see if the pre-order, if the next value is larger than the minimum value is bigger than me. If it's larger than, then that's not my right tree, so we go up. Or if it is larger than mean big, but the note value, so it's larger than mean big, and my note value is smaller than mean big, so it's not a root. So I'm not at the root. So now I always return. Now we don't return if this is smaller than mean big, right? So smaller than mean big. If it's smaller than mean big, that means it can be my right node, right branch. Or it is larger than mean big, but my value is equal to mean big. So that's like I'm at the root. So when that happens, we go in the right tree, and we move on to the next one. And we're going to build in this one, right? And then the mean big. The mean big, if note.val is not, if I'm not the root, the mean big is gonna, we're just gonna copy the original mean big. Otherwise, the mean big is gonna be the note.right. That's actually not note.value. That's actually this thing. It's actually this thing. Because it has to be the same, right? If because I'm at a root. If I go right, then the mean big, it should be the same thing. Okay, so let's build. And then how do we call it? We're gonna call it build. Right? Build, we're gonna have a root. And mean big is going to be root.val. Right? That's for the root. And after that, we're gonna return root. Ooh, what a journey. Let's take a look. I'm not confident in this one. Even if it's tree, this feels very complicated. Alright, let's try this. See how it goes. Alright, this one is right. We have another test case. Index out of range. Okay, so this one's not working. Oh, I already added self.index plus equal 1. Okay, so I cannot do that. So this cannot be this. It has to be node.right.val. Yep. Try another one. How about 1? Right, this edge case. 1 is all right tree. I want to try another one, all left tree. I think this one's good. How about all left tree? All left tree is going to be 5, 4, 3, 2, 1. Right? That's all on the left branch. Should be fine on the left branch. Yep. Let's try one more. Let's think. We'll just do this. 8, right? 5. 1, right, 7, but let's continue. 6, right? We can do 6. No, I think 6. We can do 6. That's smaller and still larger than 5, but that's it. That's the only thing we can go. So at 1, we can actually go more. We can go 1. The right tree can be 2, right? We can go all the way to 4, right? And then 4, we can go left tree, we can go 3. 3, we can go right tree. Can we go right tree? Yes, we can go right tree too, right? So it'll be 1, 4, right? 3, and 2. And then 7, now we have to go back. Now 7, right? 6, no 5, so go for 5. And that's 8 and 10. Okay, so 10. How about we add a 9? We can do 9, right? We can do 9. We can do 9, but that's it. We cannot do any more. So we go 12. 12. How about this? Oh, wow. I think it's good. I think we're good. All right, let's try this. Yep. 467 days. Well, this one's actually not easy. It took me a long time to figure this one out. I'm pretty sure I was not doing it right. We'll see. So, how do we say this? Okay, let's see. Yeah, this one, surprisingly, right? Surprisingly, surprisingly, is harder than I had expected. So how should I express this? So if I'm looking at a node, so let's say if I am currently, right? If I'm currently at a node, and I am looking at pre-order index, right? If pre-order index is smaller than node.val, it is guaranteed that pre-order index is going to be the left child of node. So hence, that is our first check in the recursive function build. The tricky part is when pre-order index is larger than node.val. And it is possible that pre-order index is the right child of node, but it is also possible that it is the right child of node's ancestor. To evaluate this, we need to pass another value, right? Another value in the build, which is the minimum value that is bigger than node.val. In other words, we pass in the value of the smallest ancestor of node that is bigger than node. Now, if pre-order index is smaller than this ancestor, we are certain that pre-order index is the current node's right child. Otherwise, we need to, otherwise we are done with the current branch and need to go back to our ancestors, right? Our ancestor for further checking. So if we are on the another tricky part is the root's mean value that is bigger than it does not exist. Hence we simply assign mean big. Let's just call it mean big, which is the mean value that's bigger than the node value. Mean big, right? The root's mean big does not exist. Hence, we simply assign mean big the same as root.val. So whenever pre-order index bubbles back to root, we know immediately that we need to go for the right branch. Finally, if we are on the left branch, right, from the left branch, the mean big is always the parent value. If we are on the right branch, right, the mean big is the same as the parent's mean big, or if the parent is root, if the parent's min big equals to parent.val, then the current node's min big is the same as its value. I think it's rolling ON. Each node is visited once. I had 47 milliseconds. It's pretty bad. All right, well, let's see some smart solutions. I feel like my solution is not smart at all. Okay, let's take a look. Yeah, we know it's on ON. Wait, is it ON or O log N? I visited each node only once. Yeah, so mine is ON. Oh my god. All right. Find the left part and the right part. Now, cursor construct. That was very simple to say. Oh, and wait, is mine ON squared? I thought it's ON, but it's actually ON. I don't know. I think it's ON, right? Because each one is only hit once. I don't know. I think it's ON because I didn't hit any of those 2 times. It's only once. Binary search. What? Root equals this. I equals bisect A0. Left 1 to I, right I to N. And then return root. Wait, hold on. How do you do binary search? A is not sorted. I don't understand. How do you do binary search? A is not sorted. Hold on. Let's maybe the question changed over time? I don't know. For an index for left part and for right part, the recursion with time complexity. Average smarter with ON time, where we give the function a bound. The maximum number it will handle. Smaller than. The right function would take the remaining elements smaller than bound. Is this our solution? Okay, so help up and down. What the hell, down and up? If it's larger, return none. If not, down smaller than this, smaller than up. Return none. Root equals this. Self, left, right, return root. Down and up. So low and high, right? If not, then return none. Okay. Then root equals prenode. Okay, so we get the current root, self-index plus 1, okay. And then, oh, this is binary search, right? Root dot left equals helper down, root dot val, and root dot right equals root dot val up. I think it's, look at this, right? We can rewrite this. Right, this one can be rewritten as, we can put this one, right? So we can just say this is smaller than this, right? It's mean big, something like this. But hold on, what are we saying? We have upper bound and lower bound, right? So we have the current value, and then we set it to root, and then the left is going to be lower bound and upper bound. Okay, right is going to be myself and the upper bound. Okay, so when we do that, we check self.index, which is fine, and then we say if the current value is outside this range. Okay, the current value is outside this range, that means it's not going to be on my branch, right? Otherwise, we can create the root, create the node, and increment it, and I do from my side. Oh, ooh, beautiful, beautiful. This is the thing. This is the thing. Oh my. I think it's all the same. Start and end. Start and end. Coming back to this. Yeah, I don't need this. I don't understand this bisect thing though. Like, how could you do bisect? A is not sorted. Are you telling me you're sorting A before you're doing this? I think this is this is the stuff. This is the stuff. Wow. I am going to redo this using I like Barbechev's explanation. It was very nice. Very good. Yeah, binary search. I know something related to binary search, right? So I need to copy and then copy this. Okay, so this is from the Barbechev. Yeah, this apparently is the correct, let's put the correct answer. Yeah, this is the correct answer. It is the correct answer with binary search in mind. I think that's the key thing. So it's a binary search in mind. So n equals len preorder and self.index equals 0, right? So def build. What do we have? We just say a low and a high, right? Low and a high. Low, high. Low and high. And then we return a tree node, right? We return tree node. So basically what we're saying is for each node, we have a low and a high. if it is within this range, because low and high is given by the parent, right? The parent say, okay, I need to look on my left, I need to look on my right. So on my left, I give a range. On the right, I give a range. And we just see if the next node fit this range. Wow, this is very, very smart. I think this is just the... Alright, let's try to write this. If self.index is equal to n, return none, right? So we were done. Otherwise, we say or low or not low smaller equal to pre-order self.index smaller equal to high. So if this or not this, then return. Otherwise, we say node equals tree node, val equals pre-order self.index and self.index equals 1. Once that's done, then we're gonna say node.left equals build, right? Low is still low, high is gonna be node.val. Yeah, that's the beauty. That's the beauty here. It's gonna be right. It's gonna be node.val and high. Once we're all done, return node. Then we're just gonna go return build, right? Minus math.inf and math.inf. I just have to import math. Yeah, that shall do. Very, very good. Okay, try it. Yeah. It's even slower, but that's not a problem. That means mine is ON, but it's just with a lot of thinking. Right? We have this mean big, whatever that stuff is, and this is just nice. This is art, right? This is art. I drew something terrible, but this is beautiful. Yeah, but in retrospect, it only makes sense, right? In retrospect, it makes perfect sense to do it this way. Yeah, shame. I wasn't able to think about this, come up with this initially. All right, that'll be it for today. We don't have time for another one, so I see you guys tomorrow. Adios.